Okay, this video is on perhaps the hardest thing that people find on vectors, and that's on linearly dependent vectors. I think students find this the absolute hardest to be able to understand. So basically a set of vectors are linearly dependent. Now I'm just going to write it down instead of just saying it because it's just so important for people to be able to understand these. Linearly dependent if, okay, and you really need to understand this. If you understand what I'm saying, then when you do the algebra it will make more sense. So a set of vectors, so whether it's two vectors or three vectors, it will only be two or three because we're only working in 2 dimensions or 3 dimensions. Set of vectors are linear dependent if one of the vectors can be written in terms of the others. Okay. In other words, we can write one of the vectors as a combination of the others, and so I'll show some examples of that in a second. One of the vectors can be written in terms of the others, and in fact it has to be linear, and I'll show you what I mean by that. One of the vectors can be written in terms of the others, and if you can't do that, if you cannot write any of the vectors in terms of any of the others, then we say that those vectors are linearly independent. And basically what we're trying to say is if we have a set of vectors, then if you can write one of them in terms of the other, then that vector is kind of useless. There's no need for it. You'll see why in a second. There's no need for a vector if you can write it in terms of the others. You can just use the other vectors to do the same job. And so we say that they're dependent on each other. They're not really needed. And so if they're not really, you can't write them in terms of the others, then they're linearly independent. And so this is really important. And so what we'll do is we'll sort of have a look at what this means more closely. So if you have two vectors. So what we're saying is that if we have two vectors A and B, what it's saying, are these linearly dependent? Well, if they're linearly dependent, that means you can write one in terms of the other. In other words, you can write A as some number times B. Like that. Some scalar quantity times B for some K, which is a scalar quantity. Okay, so that's what we can write A in terms of B. It's a scalar quantity. It's a linear transformation of B. And so I don't know if this looks familiar to you, but what did we see? Where have we seen this before? Okay, A is equal to some scalar quantity times by B, and hopefully you remember seeing this. That's when A is parallel to B. So if A is like that, and if B is like this, now let's just say B is, I don't know, has a magnitude of 6 and A has a magnitude of 2, then we can actually write A is equal to 1/3 of B. And so what we've got here is we've got two parallel vectors, and in fact what this means is that A and B are linearly dependent, because we can write one in terms of the other. A is equal to 1/3 of B. We can write A in terms of B, therefore they're linearly dependent. And so basically, let's just do another example. We've got A here like that, and we've got B like that. Can you see how there's no way we can write A in terms of B? You can't do anything. We can't write A is equal to, I don't know, 17B or anything like that. There's nothing we can do to B in a linear sense. We can't multiply it by some number to be able to get A. And so that never ever happens, and so these two vectors are linearly independent. I always do that. I'm sorry about this. There's a little button on the pen, and every time I accidentally touch it, it just does some screwball stuff. So these are linearly independent. Okay, linearly independent. So basically, if you have two vectors, if they're parallel, then they are linearly dependent. If they're not parallel, then they are not linearly dependent. Okay, so that's a really simple example. Okay, hopefully that makes sense. If they're parallel, they're linearly dependent. If they're not parallel, they're linearly independent. Let's have a look at the more confusing example of when we've got three vectors. So, three vectors. Okay, so let's think about vectors A, B, and C. And we want to find out, are they linearly dependent? Okay, so remember what the definition of being linear dependent is. Can you write one of the vectors as a linear combination of the others? Can you write them in terms of the others? In other words, can we write A as some combination of some scalar quantity m times B plus n times C, where m and n are just some numbers? Okay, can we write A in terms of B and C? That is basically what we're looking for. If you're given three vectors and you're asked, are they linearly dependent or independent, all you have to do is try and solve this particular equation, I guess, and it will give you simultaneous equations. If there is a solution, then they are linearly dependent. If there's no solution, then they're linearly independent. Okay, so I'll write that down. If there is a solution to this, therefore we have linearly dependent. Hit that button again, can't you tell? If there is no solution, that means they're linearly independent. In other words, we can't write them as a linear combination. Okay, so what I'll do now is some examples, because this is highly important, because I'm assuming you don't know what we're doing, what's happening here. So let's just have a look at this. We've got A, let's just say A is 2, 1, B is 3, negative 1, and C is 5, 6. Okay, this is actually one from your textbook because I'm just sitting here with it. Okay, so are these vectors linearly dependent or not? Okay, so can we write this as A is equal to MB plus NC? Can we write that? This is what we want to know. Can this be done? So therefore, what does that look like? Well, we've got A, let's write A, 2, 1 is equal to M. What was the vector B? 3, negative 1 plus N, 5, 6. And as you know from matrices, this gives us sort of two equations. What are they? Well, the top equation is 2 equals 3m plus 5n. Just breaking that up into its top pieces. 2 equals 3m plus 5n. And the bottom piece is 1 equals negative m, so negative m there, plus 6n plus 6n. Does this have a solution? So what we're looking for, we're just solving simultaneous equations now. Does this have a solution? Okay, so I'll just multiply that thing by 3, and so we'll get 3 equals negative 3m plus 18n, just timesing that by 3. Timing that whole thing by 3, and now I'll just add this top one and this bottom one together. So we'll get 5 equals 5 plus that, we'll get 23n, and so therefore n equals 23/5. And we'll just plug that back into probably this one, I guess, here, and so we'll get that m equals 6n minus 1. So that's 6 times, it's a bit horrible, 23/5 minus 1, whatever that is. I don't really care, to be honest, m equals, because we have got a solution. We know that n's equal to 23/5 and m will be equal to whatever that is, 120, 132 over 5 minus 1, it doesn't matter. There's a solution. A solution exists. What does that mean? That means that this is actually, they're linearly dependent. In other words, we can write A as a linear combination of B and C. In other words, that means we don't really need A if we're trying to construct things out of vectors. We don't actually need A, we can just use B and C to do the same job as A. They're linearly dependent, and so that's what happens. If we're unable to find a solution for these simultaneous equations, and sometimes you find simultaneous equations don't have solutions, then what that would mean is that linearly independent. And so basically that's all you have to do. This is the key. If you're trying to find whether they're linearly dependent or independent, see if you can write one of the vectors as a linear combination of the other two. I didn't have to write A. I could have written equally. I could have done B equals MA plus NC, or C is equal to MA plus NB. It doesn't matter. Whichever way you write it, you just have to be able to write one of the vectors in terms of linear combination of the other two. If you understand this, then you're doing really well. I'll explain it more in class anyway. Thank you.